back. Today I'm going to talk to you a little bit more about electricity, a little bit more about electrostatics, and specifically we're going to explore Coulomb's law. So Coulomb, there's a picture of Coulomb in the upper left here. Um, Obviously, he got the charge named after him, but he also, in addition to doing a lot of experiments with charge, he figured out the force law for charge, which you'll see he was inspired by Newton, of course. Volta here on the right, he got electric potential named after him. The volts, we won't get to that today, but that's further down in the presentation. Okay, so electricity and electrostatics and electric force is actually arguably the most important force in your life, perhaps other than gravity. And that's because, as you can see from this question, all the other forces that we've talked about in physics and all the everyday forces, basically if you're not getting down there inside the nucleus of an atom, other than the gravity that keeps you bound to the Earth and the Earth bound to the sun, every other force is an electrical force, right? It all comes down to charges interacting with other charges. So how do those charges interact with other charges? So this is what Coulomb came up with. On the left here, you should recognize your old friend from Isaac Newton, universal gravity, right? Two masses, m1 and m2, interact. It's a 1 over r squared law, right? If you remember the argument for that, you should not be surprised to see that electrical forces also have a 1 over r squared. Just to remind you very quickly, the idea there being that it doesn't matter the orientation of the two masses, or in electricity, the two charges, Q1 and Q2 representing the two charges. It doesn't matter if one is 5 meters above the other one, or 5 meters below it, or 5 meters to the side. What matters is they're 5 meters apart. That would be the R value. And if you think about the collection of all the possible distances that two charges could be the same, independent of orientation, you basically get a sphere, right? And so the influence of the electric field and the gravitational field are both getting smaller as the surface area of a sphere, which is 4 pi r squared. They both have these constants, capital G for gravity and K for electricity, and the 4 pi just gets absorbed in there. So thinking about the analogy there, what is charge? Is charge a scalar or a vector? So look back here. Might not know right offhand whether charge has direction or not, but by analogy, you know if mass does, right? And since mass does not, the correct answer here is that charge, like mass, is a scalar, right? It is a property of the object. You cannot point in the direction of the amount of charge it's contained within. And then what about this letter K back here? Let's go back to our equation, right? The K over here in Coulomb's law plays the role that capital G does in universal gravity, which is that it is a constant telling you basically how strong of a force electric charges can exert on other electric charges. So K is, letter C here, a universal electric constant. Now, what are the units for K? Well, just like we had to derive the units for capital G, if we look at the equation over here, we should be able to derive the units for K, the Coulomb's law constant. Let's see, we know force has to be in newtons. We know charge 1 and charge 2 are both measured in coulombs, and the R metric distance is meters. So if we solve for K, just rearranging all these units, we have a Newton here times meter squared divided by Coulomb squared. So letter D. Now, of course, you could further simplify that. That's not all in base units because you can break the Newton out into a kilogram meter per second squared and rewrite it in terms of all of those. So this isn't the only way, but it is the only correct way out of these choices. So it works great to make this analogy, and it makes it approachable. And of course, this kind of thing physicists love, to see that sort of symmetry in nature, that gravity is like electricity is like gravity is like electricity. But it's not 100%, right? There's only one flavor of mass. Even antimatter, which is a real thing, has the same type of mass as regular matter does. So there's only a gravitational attraction, right? There's only one type of gravity, because there's only one type of gravitational charge, if you will, right? Think about mass as like a gravitational charge. Now, for electricity, you already know, and we talked about before, there are two types of charges, right? Positive and negative. And so they really are opposites, and so there are actually two types of forces, right? You can attract or you can repel, which means the force law has to accommodate the fact that two charges may either attract or repel, and that's not the case in gravity, right? If you have any two masses, it's always an attractive force. We have not yet discovered any examples of anti-gravity in the universe. So here are the actual physical constants, all right? I put a capital G up here just to remind you that value is 6.67 times 10 to the minus 11th, right? So we talked a lot about what a weak force it is, and this is why, of course, you don't notice the universal nature of gravity. You know, the pencil on my desk isn't leaping off of the desk and attracted to my prodigious mass because the gravitational force is so weak, right? Electricity, on the other hand, look at that, completely opposite, 10 to the ninth, so we're up here in the billions, right? So if we have an everyday kind of level of charge, we can expect some really powerful forces. And of course, this is why electrical forces are driving all the other forces that we see in our life, and can easily counteract gravity with just a small collection of charge. Right? So the electrical force is much, three muches, stronger than the gravitational force. So why is it in astronomy, and in general, like planets, we just ignore electric forces between planets, between the sun and Earth, for example, and just model it with gravity? Shouldn't that be swamped out by electrical forces? So which of these look the best? And it's certainly not A. There's plenty of charges inside of planets, right? Protons and electrons aplenty. Electric forces, we just said, they're very strong. And letter D, the other wrong answer is they just happen to cancel out. It's because of this two flavors of charge business, right? Just because there's more charge doesn't mean you have more total charge, right? It tends to be that atoms are neutral. Why? Because they have equal numbers of protons and electrons, right? And that's true for entire planets and entire stars, right? We tend not to have, if there is an imbalance in charge, it tends to not last because this electric force is so strong. All right, let's do one example problem using Coulomb's law. So here's a classic linear one. Obviously, it works very similar to gravity because the formula is so similar to gravity. The one extra step is you have to model the attraction of the repelling. And I would recommend we do that in the beginning. So let me talk you through that. So here's the situation, right? We have three charges in a row. On the far left-hand side, we have a positive 1.1 times 10 to the minus fourth Coulomb's charges. In the middle, approximately the middle, we have a negative charge, negative 2 times 10 to the minus fourth. And then way out here on the right, further away, you can see these are the distances. Just like in gravity, we want center to center distances. So unless we're told otherwise, we'll just assume they're center to center. So the two on the left are a meter apart, the two on the right are 2 meters apart, and the charge on the far right is symmetric with the one on the far left. It's a positive 1 times 10 to the minus fourth. How do we get positive charges? Well, somebody stripped away a whole bunch of electrons, right? So the objects on the far left and the far right are short electrons, and the object in the middle has extra electrons. Okay, determine the net force in newtons, of course, on the blue charge, so the central one. And we're going to use our standard positive to mean to the right and negative to mean to the left. Okay, so just like we did with gravity, you don't solve this all at once. The formula, go back to the formula here, right? The formula only involves two charges at a time. So what you have to do is you have to pair off the charges, calculate the force due to each pair of charge, and then determine the net force.